Welcome back to class 9. We're going to do example 3.7 out of Borgnakke. And this is the heat transfer example. We won't do a lot of heat transfer, but this is some. Consider the constant transfer of energy from a warm room at 20 degrees Celsius inside a house to the colder ambient temperature of negative 10 degrees Celsius through a single pane window, as shown in this figure. And what we want to try to do, I didn't write down what we were going to try to do. So let's see what we say. What we're going to see. We need, we want to find out some more information, and they didn't give us, at least in the write-up of this, or I didn't copy it down, enough information. But let's take a look at the scenario because we have this up close. And I guess, right, so we're in this room. And here's the outside temperature. And a lot of times we'll go this T infinity for this. And this is going to have a surface temperature, and we're going to be told that surface temperature, right? So so this is 10 degrees outside, or minus 10 degrees Celsius outside. And this is a nice comfy 20 degrees inside. And we want to try to figure out how much heat is going to go through by way of convection, right? So this is a purely convection type of thing. So amongst the information that they didn't give us, they didn't tell us that the glass was 5 millimeters thick. They didn't. It's actually kind of me. I didn't. It's my fault. I'll take the blame. I made the slides. I put the notes together. I just forgot to read the thing all thoroughly. Something also that we know is that the area here is going to be 0.5 meters squared. Now this, here's a little hint or a little suggestion in the mentoring way. Somebody gives you something like that, wouldn't be so bad to try to figure out what the physical meaning is. I mean, I can picture 5 millimeters. I have a ruler. I can look that up. I can see what 5 millimeters is. But 0.5 meter square. Well, we'll take the square root of it, and what you end up with. Well, you get like a about 0.7 meters by 0.7 meters, and okay, I can kind of picture that. But then think about that in US. That's 28 inches by 28 inches, and now I can start to picture what a window looks like that's that size. It's just a little suggestion to try to make a problem seem a little bit more real. Over here on this graph, what you're seeing is we have this temperature right here, and this is in the room right here, so 20 degrees. When it starts to hit the glass, it starts going down, down, down until it gets to this surface temperature right there, right? And then within this, like some type amount of space, and a lot of times we'll think of it as a film that's going through, it's going to transfer heat out of this thing, right, and into the cold, right? And it's going to be behaving. One isn't like in a linear assumption, and more is like this is more of a quadratic assumption type of thing. So let me go to my page right here and write some of this stuff down and do the do the work. All right. So things that I was told that didn't get written onto the sheet. 5 millimeters is the thickness. The surface area is 0.5 square meters. The thermal conductivity, right? So we could probably look that up. The K of the glass, K, is going to be 1.4, and this is going to have units of watts per meter, and then degree Kelvin. This is not always degrees Kelvin. Sometimes they'll go degrees Celsius. A lot of times that's because it's just going to be a temperature difference, so it doesn't quite matter. You're just going to go delta. It's the same value if you subtract 2 delta K numbers versus 2 delta C numbers. So you're fine. All right, so that's the conductivity here. We also have the heat transfer, the convective heat transfer coefficient. It has a similar... but this is meters. This is going to be 100 watts per square meter degree Kelvin, right? This you might be able to look up easily in a table for glass. This is going to be a harder one to get because it depends on a lot of factors. You might have to do an estimation, but your situation probably isn't going to be the same. Now, another piece of information that I did not write down in terms of this is they told us what the surface temperature was right there. And the surface temperature, they happen to know at 12.1 degrees Celsius, and they were very specific about that. So if we want to take a look at the heat transfer that's taking place across the glass, right? Let's say that we know these things right here. And by the way, so we have the T of the, I guess I'll call it room. Might as well write that in there. It was 20 degrees Celsius. And the T of infinity, which is the large outside world, is negative 10 degrees Celsius. So first take a look at conduction. And we're doing these separately. Because one thing you should note is that the heat flow is going to be the same, whether it's because we're passing through here, right? So it's going to be heat flowing across this right there, and then we're going to have heat flowing across there. It better be the same. So in the way they've set up this problem, they don't really explain that. Here's our, for the conduction, it's going to be equal to these negative K. And somewhere I put the energy is leaving the room. That's why we have the K, the negative, excuse me. Ka dt dx. Notably, let's put this stuff in here. It's going to be 1.4, and let's do units right here so we can make sure that we appreciate them. And the area is 0.5 meters squared. The delta T, all right, so we could assume, or maybe I'll write this up here, Ka delta T over thickness, right? Because it's going across the X. It's the conduction is changing as it goes through across this right there. And so we'll go to the delta T, and that could, obviously this is supposed to be delta K right there. We don't have to add these things in here. We could say that this is going to be 293 K minus 273 minus, so it'll be 263, right? 263 K. But that's not going to be any different than what we would get if we take 20 minus 10, right? So it would be 30. You can see that we're still going to have 30 across there. And then the thickness is 0.005 meters. All right, so you can see that that's going to get rid of one of these, and that's going to get rid of one of these. Okay, so we're fine there. And that K is going to get gone because of that. So yes, we're going to end up with watts, which is a rate of a measure of a rate of energy. So we get 1,106 watts is what our here is, and that's the conduction. I don't know why I would just put a D there. I was thinking conduction. All right, conduction. There you go, conduction. Maybe not, because this condensation. No, conduction. That's a long subscript. Now we can go convection. And that's good. This is, I think this is the Fourier's law or whatever. And this is going to be the Newton's one. And I like Newton better, but it's just me. We're H times A delta T. All right, and so our H, as given up above, was 100 watts per meter squared degrees Kelvin. The area 0.5 meters squared. So we're going to see that's going to cancel out. And then once again we have this, but it doesn't matter, right? Because we could just go 20 degrees C minus 10. And this should put the degree C inside the parentheses. And what you're going to end up with is better answer. It should be the same thing, and it gets close to being the same thing. All right? This is convection. I guess I can go like that there. Conv. I could have gone conv up above. So anyway, these are going to be the answers for this. It's just really a demonstration of of a typical usage of these and what they physically mean, right? So you are sort of plugging in, chugging. This is some number you can, once again, this is a number you could pick up off of a graph or something, and probably be pretty. You could have a pretty good sense that that's going to be true. This is something that you gotta like assemble from a bunch of knowledge, not easily obtained, unless it's a scenario that takes place all the time in the exact same way. So then, and probably you've done experiments to determine it.